Okay, so today I plan to discuss a variation of the of counting number of lattice paths. Okay, so an important variation in the theory of counting lattice paths. Okay, in this theme of counting lattice number of lattice paths with some conditions. Okay, so yeah, so today I'll just keep the class very like bookish. We'll just go top this do it very plainly. Okay, let's just because we are doing this after a long time. So yeah, so let me state the question. It's a very simple variation, and maybe I'll start with this. So once again, we have this grid, and we again want to move north, east, and southeast. But there is a condition. We are not allowed to go below the x-axis. Okay, we are not allowed to go below the x. Now you may think, okay, another lattice counting problem, but this problem which we are doing, this problem comes in so many guises. Okay, in counting triangulations and counting other things, which we will do, that it's really very useful. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so let's keep it. It have to do 6 maybe. Yeah, so we want to again start from the origin. So start at 0, 0 and end at 6, 0. Okay, so we want to start at 0, 0, end at 6, 0, and the moves are northeast and southeast. These are the allowed moves. With the condition that not allowed to go below x-axis. Okay, not allowed to cross the x-axis, or just maybe not allowed to go below x-axis. Yeah, let's think about how many such paths are there. An example of such a path will be maybe so you can come back and touch the x-axis, but you're not allowed to go below it. Yes, exactly. No, you will need exactly 3 northeast and 3 southeast. Right. So that is again as usual. The number of 3 northeast and but we cannot make these moves in any order. That is the problem. Like if I cannot start, for example, I cannot start with a southeast moves, right? But any permutation of 3 northeast and 3 southeast will not give the answer, but any permutation will not work. What condition should the permutations have? Or should the arrangement of 3 northeasts and 3 southeasts have? Right, so that's definitely one condition. Must start with, I'll start using this notation and subscript T. That's also right. Yeah, must. Sorry, this definitely. Let's write this clearly. Must end with. So all this I'm just writing for explanation. You don't need to write it, but maybe in the beginning it will help you to also write. But if you don't need to write, you should not write it. This is just for explanation, of course. But if you do anything in between, is that good? No, in the beginning you can take 2 northeasts.
After that,
Okay. Yes.
keep the northeast and the
Mm-hmm. That will not work, right? For example, just to give a quick example, you cannot do this. You cannot make 2 southeast moves after the first northeast. You will end up going below. So this seems like a very curious problem, but see, the number is very small. It is just 6. So why don't we just do it? Why don't we just do it and get the answer? Because suppose this is in the test, right? You don't need to you don't need to know a formula. You just need to give the answer. Can we give an answer? Like we already have some conditions. We already know that it will be like this. The beginning and the end will be like this. Can we fill it up in between? Perfect. Yeah. Right. There is no choice. It won't be too lengthy. Let's do it. Let's get the answer. Let's get the number. That's right. It won't be too lengthy. So we can. And from here, you have to do this. And from here, you have 2 choices. And from here, you have to do this. So how many is it coming? Four. Okay. Okay. Five. Right. 5. Okay. Let's do one thing, because we will not be solving this problem today. This is actually not an easy question. Okay, if I tell you the trick, maybe you will understand the proof and so on. But that is not the point. It's not easy to come up with the solution of this. So with this 6, yeah, the answer is 5. Okay, let's try to do this in a way so that we learn the procedure of, you know, exploring these kind of things. Let me ask you this question. What is the smallest version of this problem? Two comma zero. No, 1 comma 0, there will be no paths. You know that, right? 2 comma 0, right? So then I'll make a table. So the smallest version is 2 comma 0. We understand this. Basically, see, the idea is that we should also learn how to explore these things, because there are countless many examples of this kind, of theory of this kind. So you should see it in a way that next time you encounter a similar thing, you can investigate on your own also. So the smallest version is 2 comma 0. So I'm just writing 2 comma 0 here. I'm not writing 0 comma 0 because we know. What will be the answer for this? Only one. Number of ways. Okay. What's the next version of this? Again, 3 comma 0 will not work. 4 comma 0. And what will be the answer for this? Yeah, right. 3. Okay, so this is okay. And so this is, yeah. So this maybe I'll just say n. Yeah. So till now, maybe we don't see any pattern, or this is too small to say. But if we write it like this, it has a lot of advantages. We will see it. Let us just explore the next case. Now you may again do this by brute force, or you may do it slightly smartly or not, but let's try to do it and get an answer. So now I'll just remove these things, this rules we know. So this you guys can try on your own and tell me. We'll do this now. We want the answer now. Is it 7 or is it more than 7? I think it's more than 7. Let's see. Let's just try again. I'll also just count. Oh, you're saying 7 because no. No. It will not be such a simple pattern. If it was so simple, then I won't be doing it. There will be 6 things in the middle. Yeah, let's think of this. Just think about this. Okay. So this will not be this. Here we have 3 NEs and 3 SEs. So it will not be more than 6, choose 3, which is 20. But it will be less than 20. So how are you guys doing it? Okay, so how many did you get so far? Mm-hmm. Yes. Okay, yeah, so that's a very important point. So extending the previous case, means that you had like this, right? In the 6th place, there will be a southeast move, right? And this one you have done it, and then this will be uniquely right. Oh, no, no, no. After, sorry, after 5. Mhm. Yes. So that will only give 5 ways. No, no, but that doesn't give a new way like this. Yes, like this. Okay. Right. So this is a new one. The uh, So you mean 10, 5, and you mean more 5, or is that okay? Okay. I think you are right. I mean, you can basically take any path. You can take any path which is like, oh, 1 minute. Yeah. Yes, yes, but we clearly see, but we see 10 at least, right? So the first 5, so first 5 is clear, right? The first 5 moves is clear. Yeah, I just say repeat the question 1 minute, but let me say this. The first 5 moves is clear. That is just the moves that end here from 0, 0 to this. So now we must ask what moves are remaining, right? So the moves that are remaining, though in those moves, we must not end up here, right? We must not end up here while crossing this line. Okay. So what are the other possibilities? The other possibilities is we are here, we cross through. So possibility 1 is cross 6, 0. Crossing 6, 0 is just the previous case, right? If you're going to cross 6, 0, that is just the previous case, so that is 5. The second one is crossing 6, 1. Obviously, if you're crossing 6, 1, you're not crossing 6, 0. And the third is crossing 6, let's write it, 6, 2. Yeah, maybe that's a way to say this. Right. Now, yeah, so now the way we can imagine is we can consider this any path from 0, 0 to 6, 0, right? And we can just shift it up by 1 unit and we can move it to the right by 1 unit, right? So this instead of starting from here, it will now start from here. Oh, okay, okay, yeah, yes, yes, yes. So yes, I will. Let me say it. We have gone a little bit far, but I will say it. Just let me finish this point. Yeah. So you can, instead of starting from 0, 0, you can start from 1, 1. So you can shift the path up, and then instead of crossing from here, you will pass through this, right? And that you will pass, it means you will pass through 6, 2. So let me just say that again. I think that I didn't say it properly. 1 minute. So if we try to focus on passing through 6, 2, okay, let's say this is the question. You want to pass through 6, 2. So if you're going to pass through 6, 2, which means this point, okay, then that means that you better make, after this, you better make this move. Right? If you're passing through 6, 2, you have to make this move, right? And you have to make this move. Okay. Is that right? Right. Oh, 1 minute. Shouting. Right. So how can we get such things? We can, so my point is that we can kind of take this path and we can kind of move it like this here. Right? You can take any path from 0, 0 to 6, 0, and you can sort of move it there. Okay, and in this way, you will get the paths that pass through 6, 0. 6, 2, sorry, that pass through 6, 2. Right? If you want to pass through this, you can, but that is not a good way to say it. I think that's not a good way to do the guesswork, because let me just see. Yeah, let's just think it from fresh, passing through 6, 0. Okay, 1 minute. So that 6, 0, sorry, 6, 0 is done. This is 5 ways. Passing through 6, 2, passing through this. So what are the possible paths? What kind of paths can pass through 6, 2? So if we, for example, make this, if we make this, yeah, the problem is, you see, this can also pass through 6, 2, right? This is a new way. This is a problem, right? What I was saying is that will not work, because you can take this kind of paths which kind of start from here and make a northeast move. And yeah, maybe you can go up and then, but as you can see, you can touch the x-axis and still pass 6, 2. So that's the problem, right? So doing this casework based on 6, 0, 6, 1, and 6, 2, well, that will not give us that. We can make it work, okay, but yeah, that will become pretty long, okay. But let's try to do that first, because yeah. So if you're crossing 6, 2, there are two ways, okay. One way is when you don't touch the x-axis, don't even touch the x-axis, right? Don't even touch the x-axis. Don't even touch x-axis. How many paths will be there of this type? Let's try to answer this, where we don't even touch the x-axis. This will again be 5. I mean, don't touch meaning that apart from the beginning and the end. Yeah, do you guys see why this will again be 5? Because don't touch the x-axis means what? Don't touch the x-axis means that after you make your first northeast move, from here again, you must make a northeast move, right? Right? And your last two moves should be southeast moves. Is that right? This case, where we don't want to, now this is independent, right? If we just, all of us can understand, right? Even joined late, you can just try to understand this. You want to start from the origin, you want to make the northeast and southeast moves, and you want to go from 0, 0 to 8, 0. And you don't even want to touch the x-axis in between. Forget about crossing, you don't even want to touch it. That means that your first two moves should be northeast and your last two moves should be southeast. Do all of us agree to this? Right? So how many ways will be there? This will again be 5, right? Because this is like, we can focus on this part. And this is the previous case. This is exactly the previous case. So this will be 5. So we kind of breaking the problem where we are not, yeah, so we are kind of going to the previous case. So this is in two ways. This is one way is not touching. The other way is in which you do touch, okay. So if you do touch, then again we can do casework. That is, if you go southeast, okay, but you are here and you want to go to 8, 0, but you want to cross through this also. So how many ways are there? So this last two moves are, see, last two moves are always fixed. That's the benefit. So can we do this quickly? How many? This will not be too many. Yeah, there should not be many, right? Because let me check it. I don't know. I think you are right. Should be right. Meaning that After move after that has to be northeast. So that again is very obvious because we are not allowed to go below. Yes, and now we can, from here, if I go south, then it's fixed. I have to go north and north, right? So that's fine, right? Oh, there are three ways. Yeah. So one way we already, okay, let's just keep it here. And yeah, so if from here, the other way would be you go up and you go up and you come down. So that's the second way, the green path, sort of. From here, there is no other way, right? What is that? Yes, that's right. Yeah, but after, yeah, that's right. That's right. I meant from here, there is no other way, only two ways, right? But you're right. The other way is we can go to northeast, then we can go, yeah, to southeast, and then we can go like this. So there are three ways. From from here, what is that? Oh, yeah, right. Yeah, right. So that's, you can go like this, then you can go like this. So we got four, right? Yeah. Oh, there are, 1 minute. Yeah, we got four. And there are four. Yeah. Yeah, because you can also go this, come down. So we are touching. Not touching, we have already counted. And then you can go like this. And this will also work. Okay, so is it okay with everyone? Just check it again. So we broke it into two cases, not touching and the not touching we did very quickly because that was the previous case. Yeah, it's a little bit of work because we are because we are not jumping to the answer. Because I mean, there is a smart way to do it, but first let's do it. Okay, so this is fine. Now let us come to the other case where we want to pass through 6,1. Has anybody already done that? Let's see. 6,1, how to do? How many ways are there? So yeah, the last case we want to do. So again, the question is very clear, even if you're joining now, in the sense that question is clear. We want to go from 0,0 to 8,0, but we want to pass through 6,1, and we don't want to go below the x-axis. Is this even possible? That's right. It's not possible. Yeah, you can just convince yourself. How will you go from here? Right. Okay. So the answer is 14. Yeah. For this case, the answer is 14. So do this for homework. Try to find this. Now again, you can do this by pure brute force, but now I would expect you to maybe take some shortcuts. Somehow find shortcuts, because when you try to find shortcuts, when you try to find good way to break the problem, then only you will, when with the maturity, you will start constructing recurrences. So this was simple casework. So basically the point is that the way I divided the problem into passing through 6,0, 6,1, 6,2, it worked, but it is not a very good way to divide the problem. That's why I was slightly hesitant, but say let's do it because that was the idea we caught up in between, right? We kind of stumbled on that idea. But it was not very efficient. Okay, it took a long time to do it, but that's fine. Do the case for 10,0. Okay. Yeah. Do it for 10,0. Try to divide the problem in different ways and do it. Okay. So the question is just Again, we know this. From 0, 0 to 10, 0, you want to go by the moves you already know, northeast and southeast, but you do not want to cross the x-axis. You want to avoid crossing the x-axis. Okay. And you can also compare this with the usual answers of all possible paths. Okay, that also you can try to compare with that and see where you are headed. Yeah, let me not say more now. Let's now do, let's do a very different problem and see if it's actually different or not. So just give me 1 minute. Which one should we go for? Just 1 minute. Yeah, let us, yeah, that's the one that comes to my mind now. Let's do this triangulation one. This is a fundamental problem, but let's just keep it simple and start doing it. So if I start with a, okay, if I start with a, let's say a square or a rectangle, we can label the vertices. And the question is, how many ways are there to break this up into triangles? Two ways, right? So with when n equal to 3, when it's a triangle, number of ways to break a triangle into triangles is just 1. For a square, what is the answer? 2 ways, right? You can do this or you can do this. Simple. This was silly. How many for a pentagon? No, you can use several triangles. Yeah, just think about this. Let me also. So you can break it up. I mean, you will need several triangles, and you know how many triangles you will need. 3 triangles, I think. Oh no, so triangulation means that you are going to partition. So the question is, partition the pentagon into triangles. The vertices of the triangle should be vertices of the pentagon. Just like you guys would have done this to count the sum of the interior angles of an n-gon. This kind of construction is done for that. Like this is an example. So how many other different ways are there? Sorry. Just by yeah. No, but you want to break up the entire pentagon into triangles. That's right. So we want to partition the pentagon into triangles. So it should be only made up of triangles. 3. Right. Okay, let's give ourselves a minute. Think about this. So someone said 3, right? 3 ways. So let's just do one. Okay, no, I can't copy paste. So let's just make another pentagon. Mhm. Right. That's right. In that way, we are getting 5, right? Because you can do this and you can do so on. This, and we can just draw one more. Yeah, so that is 5. That's right. So, right. That's right. So this, and then we can take this. And so on, right? So I think, does everybody understand, right, that this will be 5? So there are 5 ways to break it up. Yeah, but the something is wrong. The pattern is, wait, nothing will be wrong. I'm just this. Why is this 2? Where is the 3? I'm wondering. So you can understand. You can know why I'm doing this problem, right? I'm trying to show that these as 2 problems are the same. The answers are the same. This, I'm not getting this. Why is it 2 then? I mean, it is 2, but it should not be 2, right? Then the pattern all doesn't work. Yeah, and the 5 one is not. Yeah, that's right. That's also not possible. Let's keep doing this and see. Maybe in the initial few terms, the pattern is not there and just forgetting it or something like that. Let's keep doing this and it will be clear. So what's the next thing do for a hexagon? Now we have to be a little smart now. We have to do this quickly. Let's see. Like 1 already gave you 5. One kind of triangle. So basically there was only one kind of triangulation, right? In the previous problem. So here also, if we can quickly break it up into types, then we can count it. Someone has the answer. Okay. Unab, are you able to follow this one, this version? This is just about. Yeah, that's what I'm thinking. Yeah. Anyways, yeah. Yes. I will put it. Yes. Yeah. Yeah. But this is basically, we have this hexagon, let's say, and you want to break it up into triangles. And how many ways are there to do it? Okay. So for example, this is one way. So, but let's not start with this. Let's start with the kind of the way we already had, right, which is from one vertex you do. Right. So there are 6 of this type. Let's just write it here only. 6 of this type. Let's make it a little small. Right. What is the other way? Yes. And how many ways will be there? How many members will be there in that type? It should not be 6, should be less than 6, I think. Sorry, the other two? That are not connected. Okay, let me name them. Okay, yeah. So I think in that way we get 6 of this type also. Is that right? Mm.
So we get the 6.
1, 3, 6. You mean joining 1 and 3? You mean like this? Mm. Yeah, yeah, like this maybe. Yeah. So that will also give you 6 because there are 3 pairs of opposite sides, right? So for example, this one we can say 6, 5, 2, 3, right? If we choose these as the opposite sides, then there are 2 z's. And so this pair of opposite sides is giving 2, and in this way you can get 6. So this will also be 6, I think. So just writing 6 ways. Is there any other way, any other type which is not as said like this, and also not everything is coming from the same point? Okay, let's think about that. Yeah, 6, no, 6. Oh, no, but that will not be a triangulation. So you see, the vertices of the triangle should be the vertices of the hexagon. Right? If you're thinking about this, right, this is not allowed because, yeah, the middle vertex is not. So is there any other type? Let's think about it. So is there any other type of triangulation? Let me just redraw this like this. That may help you to think in a different, yeah, let me just draw it like this. So these are the 2 types. So I'm doing casework on the vertex 1 kind of. What is the other way? What could be the other possibility around the vertex 1, the lines coming from 1? Yes, exactly. That is the, yes, right, right. That is what is left, right? And that is the only thing that is left. Now, I will not say how and so on. Just think, you can think of it in so many ways, that this is the last case work. You can just think on situation for 1 from 1, 3, and then on based on 2, there is close and then outside. You can think in many ways. Yeah, just yes, that's the only other one. Absolutely. So there are 2 of this type. So you see, we don't have a formula for this again, but we are kind of getting a hang of it in the sense that there are 3 different classes, and yeah, we are generating it based on rotations and so on. We are not saying all that abstractly, but we are doing it. So as you understand, this is again 14. Again, for homework, do this for no. So this will not be 8, this will be 7. That's right. Okay, this will be 7, and try to see what you get here and try to see what you get here. Right. So that is that. That is there. So this pattern of 1, 2, 5, 14 or 3, 5, 14 has appeared again. Yeah. So 1 minute. So instead of trying to explain this, because explanation will not be simple, let's do another kind of problem. Okay. And there also we can try. So I'll just remove this because this pattern is already there. Screen. Now there are many problems which give the same answer, but I have to think of something which is simple. Just 1 minute. There was something related with trees, I remember. 1 second. 1 minute. Yeah, anyways, leave it. That tree thing, it's a little, can get a little confusing. So the other way is, yeah, let's think about this. Suppose you have A1, A2, A3, okay, 3 numbers. Okay, let's say that there are 3 numbers. 1 minute. Yeah. So if there are, no, okay. So if you just start with, let's say you take X and Y and you add them, okay, and then let's say you multiply this with Z, okay, and it's a complicated expression, so you have to further, let's say further you have to multiply this with the sum of 2 things, let's say A plus B, and this could be numbers or whatever. Yeah. So you'll have to put so many brackets, right? And let's say you'll have to divide this entire thing by some C, right? Sorry. Right. So you see, we had these quantities where we are multiplying a few of them, We are adding a few of them. We are dividing. But to make sense of this expression, we are putting some parentheses, right? Now the parentheses have to be put in a certain way, right? If a parenthesis is opening, then it has to close. I mean, obviously, right? If a parenthesis is opening, it has to close. But then the parenthesis that opens later, it has to close first before the earlier parenthesis closes, right? For it to make sense. That right? For example, how can I mess this up? I can, so by keeping the same number of parentheses, certainly, I mean, there are so many ways you can mess this up, right? You can, I mean, you can, if you do this doesn't make any sense, right? So with when you have an expression and you're putting brackets or parentheses, yeah, in smaller grades we put different kinds of parentheses so that we are clear about it, but we understand that they have to be put in a certain way, that there is a certain rule. Let's not say that rule very clearly and so on, because we kind of understand it intuitively. Okay. But we understand that because there are certain conditions based on how we parenthesize an expression, some parentheses, some parenthesizations will be legal and some will not be legal. Okay. So we have legal parenthesization, okay, and we have illegal ones. So just to make this very clear, let's say we start with, six, we can start with six pairs of parentheses. Yeah, so we have 1, 2, 3. Hold on, no, I meant 3 pairs. Let's only take 3 pairs for the time being. Yeah. So how many ways can you, kind of use them to parenthesize things? How many different legal parenthesizations can you create? Parenthesizations can be created. You no, so the number will not be really important for us, right? The number will not be important because that's not going to, yeah, that will not really change if it's illegal or legal. So essentially what we want to do, we want to arrange these parentheses. So for example, one of them is, this is perfect, right? Now what number we put, that doesn't really matter. If you put A, B, C, and you put some operation, that we are not interested in. That's a, we can just put multiplication itself only. But this is one particular, this is legal. You, by looking at it, you can say, okay, this is fine. It's working, it's good. But for example, this will not work. This just looks wrong, right? It is just wrong. Mm-hmm. No, certainly not. This is obviously not legal. Right? You have to use all of them, and in the sense that you have to use all of them, right, to create a legal parenthesizations. Right? See, in any legal parenthesization, number of open brackets has to be equal to number of closed brackets. They can't be different, right? Oh yes, yes, of course that is legal, right? Any, yeah, why should this not be legal? You can convince yourself by taking an example, right? You can just take a plus b multiplied by c plus d, right? E plus f. This is perfectly legal. Yeah, and this is also good, right? That first I started an operation, I started, then I multiplied, then I finished multiplying, then I had to divide. Let's say this is fine, or let's say dividing by c plus d. Mm-hmm. Uh-huh. It is similar, but it is a little more difficult because here all the open parentheses are same. They are not distinct. So it's harder in that sense. Yeah. Yeah, there is a problem. And also it's not enough for it to just come before. There is certain other kind of thing. So what makes a parenthesization legal is a question that one can ask, but let's just quickly first count. Let's not get into the deep thinking and so on about this nature of this, but let us just count. See, for n equal to n means number of pairs. If you have only one pair, then there is one way, right? See, by n equal to 1, I obviously mean one pair, because obviously one open bracket is doesn't make sense. One pair, one means one pair. That's just one. If you have two pairs, then how many? Uh, two ways, right? Two ways, right? Yeah, because it's just like this, or you can just do this nested or like this. And these two are legal, and two ways. Okay. What about three? Let's do this. Let's just get the answer first. One. No, when there are three, when there are three pairs of parentheses. No, not only two, more than three. We already wrote kind of three. Yes, yes, three pairs of parentheses, right? Because three bracket three does make sense. Three pairs, yeah. See, we can. This is different. Remember, this is different from this. Four. Okay, yeah, this is already there. One more. Or is there any more? Ah, right. That was missing, right? Okay. So this example probably will reveal more. You can do any one of you feel any similarity of this problem with the first problem? Not just in the answer. Okay. So try to see a similarity. Hmm. Mm-hmm. Oh yes. For two pairs, right, right. So right. So in that way it is similar, right? But do you see how it is similar to the lattice counting problem that we started with? Uh, yes. Yeah, or yeah, you can say, yeah, it's kind of reducing in the same way. That's right. Right. And anything else? See, for a that's an interesting point. Is there anything else also? Yeah, let's see. Now we are getting, so we want to end with not just knowing that the answers, we want to end with saying that, look, these two problems we don't know how to solve, but I, but we can say that they will have the same answers. That is what we want to say in the end, right? So see, what did it mean? Let's me, you guys think, let me write a few things, then I'll say. The answers are coming out to be same and so on. We are seeing kind of some similarity, but yeah. Second one is a little, it's not so easy to see how that is directly related. It's more surprising, but certainly we want to understand this. Number of legal parenthesizations. We want to see the connection. Parenthesization versus number of paths not going below. We want to understand the comparison between these. So let's just come back to the number of paths because that's a more familiar thing. See, if we want the paths to not go below the x-axis, what does it mean? Suppose there are 3 northeast and 3 southeast. See, not going below the x-axis basically means that at any stage, the number of northeast moves is at least as much as the number of southeast moves. Yeah, does everybody see that? At any point in the journey, right? So at any point, number of southeast moves is not more, never more. See, this is the very meaning of not going below the x-axis. Okay, and let's not say more there that you think while writing. Here, when you have 3 parentheses opens and 3 closed, what is the key to, what is the key to getting a legal parenthesization? Similar to what we already have written for number of paths. So we already have drawn a few of them above, so you can use that. And think what similar condition can we put on legal parenthesization or on parenthesization to be legal? Similar condition as we have put. Yeah, that is certainly there, but anything more? Like here we know that we need equal number of northeast and southeast, but that was not enough, right? We needed a more condition that at any point, number of southeast moves can never exceed the number of northeast moves. Otherwise, you'll end up going below the x-axis. Can we say something similar for parenthesization? Yes, exactly. At any stage, the number of closed parentheses cannot be more. I mean, you cannot close more parentheses than you have opened. Right? And that is the only condition, right? So basically, and you can think about that. You can say this more clearly while writing. Yeah. So it's just similar condition, same condition. There's literally no difference between these two things apart from just here in this world we are calling parentheses open parentheses, in that world we are calling northeast, in this world we are calling close parenthesis, in this world we are calling southeast moves. I mean, just a different name, right? But the essence is the same. The real matter that we are interested in is the number. That is the same, and it's not just that the number is same by accident. There is a certain pattern, right? It's just the same thing apart from the naming. So now do you guys agree that the answer to these two questions will be the same, right? If you have n pairs of parentheses and here you have 2n comma 0. I mean, you don't know, we don't, let's say we don't know the answer to this question, but we know that the answers will be same. Would anybody like to explain that? Does anybody find this surprising? That the answer to these two questions are same. I mean, I want to say that it's not surprising now. Okay, okay. Mhm. And every open you have closed, but but you see here also the second condition is that at any point the number of southeast moves should not be more than number of northeast moves. And here also we know, right, that number of, again, at any point. So then these two things, aren't these two things then exactly the same? You see, there is no difference, right? At any point, the number of closed parentheses, I mean, just replace closed by southeastern. Point, the number of closed parentheses is not more. Now you see there's no difference between these two questions. So if you are going to create a legal path here, which is you're going to take northeast moves and southeast moves, but you're just going to make sure that the number of southeast moves never becomes more. It can become equal when it touches the x-axis in the middle sometimes, if it does. Right? But then for this, you have a parenthesization also. Open, closed, open, close, close. And you know what is happening. Closed is south moves and open is north move. And there is the same condition that number of closed parentheses should not become more than number of open at any stage. And here also condition is same. So if you just call this open and you just call this closed, then it is the same thing, exact same question. So the answer will be same. right? So when there are n parentheses, then for any legal parenthesization, you can replace the open by northeast and closed by southeast, you'll get a legal path that doesn't cross the x-axis because the same condition is met. It's the same thing, just different names. So the answer is going to be the same. So this is the first example of the phenomena of bijection principle that we're seeing. And it's a tremendous tool. As you can already see, right? We have no idea what the answer to these questions are, but we know that the answers are the same. Okay. That is, let's just take a minute and see if this is clear. If something is not clear, please say. Okay. Yeah. Then we can go to the next question. Right. Okay. Good. So this is the thing. Now you already have the task laid out for you. Do that. I do not think I should go into more variations today. Mhm. Yes. It is like filling number of ways to fill the blank spaces. So these are all counting problems. Exactly. These are all counting problems. Obviously, these are harder ones, but these are all counting problems. But here we are doing something more subtle than just, we are not, so today we didn't actually count, we didn't give formula for a answer, but we said that two counting problems whose answers we don't know, but we know that their answers are same. Yeah, so this is a strange, slightly different thing, but this will keep happening. Okay, so this is basically a set of all paths, and this is a set of all parenthesizations, and we want to know the size of the set without actually listing out all the elements. We want a formula, but the same set has two different decorations. One decoration is in terms of the language of paths. Some people are talking about the set in the language of paths, giving a meaning to it, giving a way to talk about it so that we can count it later on. We'll see, we'll use it. And then the other is the parenthesization. Yeah, see, they are the same sets, but it just they have different decorations, right? In this, so here, yeah, right, they are the same set, path 1, path 2, some set, some number of things are there in this, and here also some number, all legal parenthesizations, but but as sets they are the same kind of, but they have different decorations, and some decoration may help you to count it easily, some may not. This is a geometric decoration, right? And this is a, we could, some, it's algebraic, right? So some of it may help you to solve it. Okay, and then we had a third thing, that was triangulations. You see, so we will prove later on that this also gives the same answer. I mean, we already kind of saw the pattern. So, and then we have other problems, many problems which will give the same answer. Okay, and what does it mean? It means that if you can learn how to count one of them, if you can figure out how to count one of them, then you have counted all of them. Is that right? Yeah. Yeah. That is hard. That's right. A lot of times this happens. A lot of questions are open problems. Nobody knows what the answers are. But you will see that there are many problems which have the same answer. Okay, that is what we do. Yeah. That's the next best thing to knowing the answer. So that is the thing. Yeah, let us just stop here today. I think just we'll get more if we do. Or from the last time, if anybody wants to do a problem, we can do that I had given the last time. If anybody has tried, well, I think this is okay. We have did 3 variations. Now you can fill in the blanks that I asked. Anyone has tried the previous problems and wants to discuss any one of them? Okay, then I think we'll stop. Please try them if you haven't, and maybe next class ask me. Okay, I will try to take a class on Sunday. I think I will take, hopefully. Okay, I'll confirm.